tilt away from the plane, which is the ecliptic, the Earth-Sun trajectory that defines the orbital plane by the Earth. And a few degrees of tilt is sufficient to take Mercury from passing in front of the face of the Sun, unless the alignment just happens to be just right. And the same is true of Venus, and in the case of a Venus transit, it takes a century for the transit to recur.
Chris, I'm sorry. I think that our audio has not been working up until
okay.
now, so we may have to start over.
Okay.
I'm terribly sorry.
Okay,
this
go
is
ahead.
again kind of a remnant of our technical glitch.
Yeah, sure.
So why don't we go back to the first question?
Is it working now?
I believe so. Okay. I can hear it now.
Okay.
So let's just go back to Rami's question and talk about what methods are currently used for exoplanet detection. Again, I'm terribly sorry.
So we had an audio problem, so I'm going to repeat the answers to the first two questions. Exoplanet detection has been primarily done in the last 6 years by the transit method or the eclipse method, where if the orbital plane is almost perfectly aligned to the line of sight, then there's a significant chance that a planet will cross the face of its parent star, causing a very slight brightness dip in the star for a short period of time. That's a transit or an eclipse. The Kepler satellite, a 1-meter telescope in space launched by NASA in 2009, was stunningly successful in detecting transits or eclipses, and has found over 3,500 exoplanets. The total body count of exoplanets is around 5,000, that is candidates, most of which are likely to be really there. Most of the rest have been found by the Doppler method, which is the indirect method of finding a planet by its tug on its parent star causing a periodic Doppler shift. There's also a wobble that could be detected, but that's too small to be directly seen. A third method is direct imaging, where you look for the feeble reflected light of the planet sitting close as it is to a star that's hundreds of millions of times brighter. That method is not a good way of finding exoplanets in general, but has been used to detect 50 or 60 of them that have already been found by other methods. And a final method that's a little esoteric and a kind of a niche method, but is very sensitive to low-mass planets, is microlensing technique, and that's only been able to find 10 or 12 planets so far.
All right, and then the second question, which we can go back to now, is why is it that we don't see transits of the inner planets twice a year?
Right. So in principle, both Mercury and Venus, which are on interior orbits to the Earth, should potentially cross the face of the Sun, and a Mercury transit just happened yesterday or a few days ago. Mercury's orbit is about 88 days, which is about 3 months. The Earth's orbit is, of course, a year, so that implies that several times a year there should be a Mercury transit. But of course, we don't see it several times a year. It happens about once every 4 years. The next one is going to be 2019. And it's a good question as to why not. The why not is because the alignment and that transit really does rely, for objects that are separated by tens of millions of miles in space and that are physically quite small, relies on a very exquisite alignment between the three objects. And the planets in the solar system do not all orbit in exactly the same plane. We can call the plane of the solar system the plane defined by the Earth-Sun orbit, which is the path of the Sun is called the ecliptic in the sky. And we can ask, what is the orbit of Mercury relative to the ecliptic? And it turns out it has a tilt by a couple of degrees. And that tilt is enough for most of the potential transits to take it away from crossing the face of the Sun. Because again, the Sun is 100 million miles away and is a fairly small object. So Mercury is not necessarily going to cross the face of the Sun unless the alignment is really exquisite. So that small tilt of the orbit of Mercury and Venus relative to the Earth-Sun orbit is sufficient to make these transits quite rare. In the case of Venus, it actually makes the transits occur in pairs separated by almost a century. So those are exceedingly rare events.
Right. The next question is kind of related to both of these, actually. And what about detecting planets if they're too small to pull on their host star or had too inclined an orbit? What if you were looking for Mercury-sized planets? Is that possible around other stars?
So it's a good question. What is the limit for exoplanet detection right now? And the answer is different depending on the detection method. It is true that the transit method only works if the alignment is almost perfect. In other words, the planet is orbiting in a plane that includes the line of sight to the star. If the tilt is 90 degrees, there's not going to be a transit. In fact, if the tilt is more than a couple of degrees, there's not going to be a transit. Now, that's not a problem. It just means that you have to correct your detection statistics for the fact that exoplanet orbits are randomly oriented in the sky, and you're only able to detect some fraction of them. It doesn't affect your overall understanding of exoplanets. It just means you only ever detect a fraction of them. The smallest exoplanet that can be detected by the transit method is a little less than an Earth size, remembering that transits detect size, not mass. So Earth is not the limit. Probably something like Mars is the limit with transits, and people have tried to work that technique down to sort of Earth, a Moon or Mercury-sized objects without success. So Mars is essentially the limit for transits. For the Doppler method, the limit is a little higher. It's actually proving hard to get the Doppler method into a realm where it can detect Earth-mass planets. And that's because the tug of an Earth on a star is so small that that velocity corresponds to the typical motions of gases, plasma, in the atmosphere of the star. So you can be confused by turbulent motions in the star atmosphere masquerading as the tug of a planet or a periodic Doppler shift of a planet. So the limit on Doppler detection looks like about an Earth mass. For direct imaging, if the planet was sufficiently far away from the star, the detection limit also may be roughly like an Earth, because it relies on a significant angular separation between the planet and the star. But most planets are not found this way. It turns out the most sensitive method is the fourth one, the niche or esoteric method I mentioned earlier, which is microlensing. Microlensing relies on the fact that stars are distributed in three-dimensional space, and every now and then a star that's closer to us is just going to pass in front of a more distant star. If that passage is perfectly aligned, then by general relativity, the background starlight will be magnified or lensed by the intervening star that crosses the face of the background star. And so for a short period of time, typically days or even hours, the background star's light will be magnified. If in addition to the foreground star causing a magnification, that foreground star has a planet orbiting it, it'll cause a momentary secondary amplification, which is even quicker because the speed or time scale of the amplification depends on the mass of the object doing the amplifying. If you work the math, in principle, microlensing could actually find moon mass objects. It has the potential to find things substantially smaller than the Earth. It hasn't done so yet, but people are optimistic that it might.
All right, the next question is from Lori, who may or may not be on with us live. What is the evidence that there is a connection between dark energy and dark matter?
Dark energy and dark matter are the two enigmas of cosmology. They together contribute 95% of the universe, with the remainder being normal matter, the kind we're made of, which physicists will call baryonic matter. At the moment, there's no good evidence that dark matter and dark energy are connected in a profound physical way. But always we should put a little caveat or asterisk by that statement, because we don't know at the moment what either are. There's a good suspicion that dark matter is a new form of fundamental subatomic particle, possibly the most stable supersymmetric twin of a massive particle predicted in fundamental theories of particle physics. It may, in fact, be detected in lab experiments or accelerator experiments in the next few years. Dark energy, we have no such supposition. It's really quite a mystery what dark energy is. And in terms of their behaviors, one sort of repulsively with negative pressure causing the universe to accelerate, and the other being distributed on larger scales than matter, but forming clumps of material in the way that normal matter does. They really behave in quite opposite ways. So many physicists don't really think there's a deep connection. It is, however, a little mysterious that in our universe, these two entities have almost the same strength. Now, to an astronomer, being similar within a factor of 2 or 3, it means almost the same. And what's striking about that is in the entire history of the universe, this is the first time that dark matter and dark energy have had about equal effect on the universe as a whole. For most of the previous history of the universe, the dark matter was dominant because the density of the universe was higher, and so the gravity of all that dark matter was stronger, decelerating the universal expansion. For most of the future history of the universe, dark energy will be ascendant and dominant. As matter thins out, then the accelerating capabilities of dark energy will dominate. So there's some strange coincidence leading to these two entities being so physically similar in their strengths right now as we measure them. But that itself, of course, could just be a coincidence. It doesn't mean there's a deeper connection between the two entities.
All right, the next question is again regarding the Mercury transit. What can we learn about Mercury from these kinds of transits?
I'd have to say that Mercury transits at this point are of interest, to amateur astronomers, the general public, if you get to see it. We had an exhibit out on our mall at the U of A. It's been nice and clear this time of year, so people were observing the Mercury transit on the university campus. So it's a way for the public to get engaged with astronomy and see something remarkable. Actually, Mercury is tiny. Some people are slightly disappointed when they see how small Mercury is, appearing like almost a little speck slowly moving across the sun. Astronomers are not going to learn anything new about Mercury from these type of observations. We've known what its orbit is for a long time, and therefore we can predict these transits. And Mercury, of course, now has had a close passage by a NASA spacecraft that has observed it in quite a lot of detail for the first time, actually, in the last few years. So that's given us much closer and more detailed information than we could ever get by observation through any telescope. So I think the Mercury transit is a great event for raising public interest in astronomy, but it doesn't really have a research purpose for astronomers anymore.
All right, the next question is from Rami regarding the SpaceX controlled ascent and landing of a rocket. Is it really fuel efficient to do so in an earthly atmosphere? What other methods are suggested, tried, or even used?
So SpaceX has had a very recent success, its second success of re-landing on its launch platform, an offshore launch platform. It's offshore, of course, for safety reasons, because SpaceX has also had a couple of mishaps trying to re-land one of their rockets, and so if they still have fuel on board, they're going to explode and be quite dangerous. Is that sufficient to transform the model for the space industry? Well, the reusability does transform the economics of getting into Earth orbit, because the thing that made the shuttle and most of the previous spacecraft from the 60s, 70s, and 80s so ruinously expensive was just jettisoning various stages of rockets, and even if you could recover some of those stages, that was an extremely expensive and time-consuming maneuver. So SpaceX has got a rocket model where it's fully reusable, and in principle that reduces the cost substantially. However, and relative to the question, the fundamental problem of all of these rockets, whether it's the Blue Origin spacecraft designed by Amazon founder Jeff Bezos, or not by him, but by his team of engineers, or Elon Musk's SpaceX, these rockets are still using chemical fuel. They're essentially using a very volatile form of kerosene, which is the best form of sort of petrol or petroleum-based chemical fuel we've come up with. But rocket fuel hasn't really changed for decades, and as a chemical form of energy, it's literally millions of times less efficient than nuclear power would be, fusion or fission. So all of these methods for getting into space are essentially inefficient because they rely on chemical energy. And so you're lugging a large mass, a heavy weight of fuel into orbit and trying to squeeze as much energy as you can from it, rather than trying to get an enormous amount of energy out of a tiny amount of fuel, which is what would happen with nuclear power. That said, these wringing all the last efficiencies you can get by reusability, by using super light, super strong titanium, aluminum alloys for building your rocket, and so on, and operating at very high temperatures, extremely high nozzle velocities, I mean, just very high degrees of engineering in the rocket design itself, have squeezed enough efficiency to drop the launch cost per kilogram or per pound by factors of 5 to 7 compared to before SpaceX and Blue Origins were doing their work. And that will really be a game changer in the exploration of space. So yes, they're still relying on an old technology of chemical fuels, but even so, they're going to change the game by being reusable.
All right, the next question is, what is the most useful way, what is the most useful way to use the information about gravity waves that we have from LIGO?
So we are waiting for LIGO's next set of detections. Remember that the LIGO, the LIGO event that caused enormous excitement just a few weeks ago, it's hard to imagine it was that recent, derived from test data. Actually, it was taken during the very end of the test phase before LIGO started taking science data. And the LIGO team are being very cautious about reducing their data and being sure of their results. So we can expect in the next month or so to start seeing more events from LIGO. What we typically learn from LIGO event, as we learned from that first one, is when the event is detected at both LIGO sites at Hanford and Livingston, then we get a time delay between the two signals, and also a slight difference in the strength of the signal, the amount of squeezing of space-time, if you like, at the two locations. And that small difference in strength of the signal plus the time delay actually gives you a direction. They let you say which part of the sky the gravity waves came from. In the case of that first event, it was a direction in the southern skies, roughly in the direction of the Magellanic Clouds. That's not sufficient to isolate the actual originating target, and in the case of a galaxy that's 1 billion light years away, there's so many galaxies, faint galaxies in a big patch of sky, there's no way you could figure out which one happened to have two black holes colliding all that time ago. But that's the beginning of how you would isolate an actual specific event. So when there's a third LIGO detector, and a third one is being built in the French Alps, and a fourth one is being planned by the Japanese, and there are other, it's now become a booming industry, of course, with that first success. The more LIGO detectors you have of equivalent sensitivity, the better your directional pinpointing of the source of the gravity waves. And so with a fourth and a fifth LIGO detector, it will start to approach the situation where you can actually start to say a fairly small patch of sky, which might be associated with a single galaxy or a supernova going off or some other cosmic event. So having more LIGO detectors will increase the amount of the information. Even so, the characteristic signature, this ringing signal, this oscillatory and then damped signal, is so characteristic of the event that there's no doubt as to what's happening to give those gravity waves.
Right, the next question is from Lori. And the question is, what is the best, quickest way to get a job in the field of astronomy? And she's asking as somebody who is a late career, retired high school teacher in humanities.
Well, astronomy is kind of a niche profession. Most astronomers get their primary training in physics or mathematics or sort of related field, physical science basically, and then move into astronomy. Some people start with undergraduate degrees in astronomy. We have such a degree here, and there are other places. So obviously astronomy is very closely allied to physics and math, so any astronomer, professional astronomer, will have a pretty strong training in physics and math as well as astronomy. And to get a job as a professional astronomer or to go to a graduate program, that's the kind of background you're going to need. Coming from humanities or social sciences, that's challenging, of course, because you're going to have to go back and hit the books and do calculus and do basic physics, and it could take a while. Now, not all jobs in astronomy actually require that level of training. To work as a research scientist in a major observatory or a NASA center, or to get a faculty job in astronomy, you need a PhD in that subject or a related subject. But of course, there are other jobs in astronomy. There are jobs at major observatories, there are jobs at research labs, and there are jobs at some organizations that build telescopes and operate telescopes, like the Smithsonian Institution and so on, where people are doing astronomy that don't necessarily have that degree of technical training. They're working on other aspects of the subject. And then obviously in the educational arena, you need a base level of knowledge of astronomy to be able to teach astronomy. But at the level of schools, For instance, the teacher credential plus a certain amount of math, physics, and astronomy will be quite sufficient to teach astronomy in the schools. And you can also get involved in outreach and other kind of programs where you just need some minimum amount of astronomy that you can pick up from a few courses, I suspect, and then you can contribute to that kind of effort. So there's a landscape of professional astronomy jobs, not all of which require advanced degrees in astronomy.
All right, next question is from Tyler. Do you think that Mars will be habitable one day? And will we continue sending humans there and make life grow? Is it even a possibility without a magnetic field protecting the planet?
So that's an interesting question, the long-term habitability of Mars. So obviously, in the short term, our ability to be there for any length of time and have a base will just rely on creating little bubble environments where all the materials we need to live are generated locally, where we mine the soil for oxygen and water, and we grow our own food. And that's not really making Mars habitable. That's sort of eking out a living on Mars just by ingenuity and by using the raw materials to survive. The question of Mars being overall habitable is something that has been considered. It's called terraforming, the idea of deliberately altering the entire planet to make it potentially habitable. That's a science fiction idea, but actually engineers and NASA people have studied this in a fair amount of detail. And the mechanism for terraforming Mars, or making it habitable by humans, is actually well known. It's extraordinarily difficult, expensive, and time-consuming, but it's not impossible. Basically, there's 3 stages you would need to make Mars habitable. As you pointed out in the question, Mars does not have a magnetic field, and so it's got a huge amount of incoming radiation, ultraviolet radiation, damaging cosmic rays. So Mars is not going to be habitable unless you have a protective atmosphere anyway, and its atmosphere currently is about 1% of the thickness of the Earth's atmosphere. So the 3-stage process involves somehow raising the surface temperature of Mars by about 10 degrees C, sufficient in many places for water to become liquid, especially at the right time of the seasons, and thickening up the atmosphere, simultaneously thickening up the atmosphere, which is made of carbon dioxide, with more carbon dioxide so that you kick off a mild greenhouse effect. The greenhouse effect, of course, is a positive feedback loop where the heat traps the atmosphere, carbon dioxide as a greenhouse gas traps the radiation, which could liberate more carbon dioxide, which further thickens the atmosphere, traps more heat, and so on. That's the accelerating cycle, because remember that carbon dioxide is bound up into rocks and can be released by heat. So the engineering approach here is to dump or liberate by explosives, is one way to do it, just a lot of bombs, a lot of carbon dioxide that is currently bound into rocks into the Martian atmosphere, thickening the atmosphere up and kicking up a little greenhouse effect. If that gets underway, then a lot of that subsurface water that's now ice will liquefy, and you'll start to have water on the surface, something that hasn't happened on Mars for about 3 billion years. Second, this is all the first stage, and this, of course, would take probably centuries, or, I mean, unless you spend a huge amount of money and resources. The second stage involves starting to make Mars a living world. Now, Mars would still be a pretty unpleasant environment at this point, and no breathable air, of course. And so you'd see these now bodies of pretty frigid liquid with extremophiles, with microbes that could metabolize and using respiration could generate oxygen. So you'd have oxygen producing microbes, and you would start to generate your oxygen, your breathable atmosphere that way. But you're still just clinging to the edges of life, because these are microbes that can handle pretty extreme conditions. You would also continue with your greenhouse effect. You continue to thicken the atmosphere up, but obviously you want to start changing the balance between carbon dioxide and oxygen. And you probably, to make it truly breathable, you'd need a buffer gas, which on the Earth is nitrogen. That also can be generated from rocks, or it can be generated also by plant life. So that's another reason to see Mars with life. And then the third stage involves altering the mix of the atmosphere while continuing to thicken it to move it in the direction of a breathable atmosphere. So less carbon dioxide, more oxygen, more of a buffer gas like nitrogen. And this is all going to take a very, very long time and cost an enormous amount of money. So it's barely into the realm of science as opposed to science fiction, but there are actual engineering studies that have shown that it is possible in principle.
Right, the next question is from Will, and the question is a 30-meter telescope project for Mauna Kea twice as good as a 15-meter telescope? Is there a law of diminishing returns at work here?
The 30-meter telescope of the University of California and Caltech is a mosaic. It uses essentially the Keck idea of, which is like 1.2 meter, I think, hexagons, and Keck has 36 of them. This 30-meter telescope has over 400 of them. I don't remember the exact number. So it's just scaling up that idea of hexagonal individual mirrors that are working in concert through laser alignment and a neural net and feedback loops and so on. If there are not too many gaps between the hexagons, which usually there wouldn't be, then a 30-meter telescope has 4 times the light gathering power of a 15-meter because it goes as the square, it's the area, so it goes as the square of the diameter. And that's quite a big factor in astronomers' units of magnitudes, of 1.5 magnitudes. So that's a significant extra light gathering power, which in cosmology or looking deep into the universe corresponds to a significant amount of extra depth or volume that you can probe. And that is worth having, and that's part of why astronomers are always hungry for larger and larger telescopes. As far as diminishing returns, there is, in a sense, a law of diminishing returns, and the diminishing returns come because of the cost. As you build bigger telescopes, those telescopes have to be contained in buildings, and they have to be held by structures, and they have to be moved around the sky, and their mass goes up. And even though your light gathering power is going up as the square of the diameter, the volume of the building you build and the mass of the structure that contains it is a 3-dimensional entity. And so the cost at some level is going up faster than the square of the diameter. In formal terms, when people study this, it's going up as the 2.5 power of the diameter. In other words, the cost is going up faster than the light gathering power is going up as you make telescopes bigger. And that's the bottom line of diminishing returns. It just means that yet larger telescopes than 30 meters or the 22-meter telescope we find here called the Giant Magellan is going to be really difficult to do because these 20 and 30-meter telescopes are already billion-dollar projects, and I don't think anyone will have the stomach for spending $10 billion on a huge telescope.
All right, the next question is, right now, traveling to other star systems seems to be quite inefficient and time-consuming, for example, Alpha Centauri. What forms of propulsion do you think could possibly allow us to travel efficiently to different star systems in the future?
Yeah, star travel is really beyond the pale. If we take the fastest spacecraft that humans have ever built, which actually is kind of a venerable one, I think it was launched in the 70s as the Helios spacecraft that was moving towards the sun and sort of swung through the inner solar system and picked up a lot of speed. If that spacecraft headed out of the solar system, it would take 50 or 60,000 years to get to the nearest star. So based on current spacecraft technologies and actual speeds, we're tens of thousands of years to get to the nearest stars. That's clearly not going to excite many people. That's just too long to be interesting. I guess the best recent example of people who are planning to do something different is the Breakthrough Starshot project, which got a very splashy press release and news conference about a month ago. It's Stephen Hawking is heavily involved. Mark Zuckerberg is involved, Facebook CEO and founder. And Yuri Milner, a Russian entrepreneur and billionaire, is sinking $100 million into it. So the Breakthrough Starshot is trying to get beyond this speed limit that we have on existing rockets by going miniature. Essentially, they're trying to miniaturize sensor technologies into a tiny little package. Just imagine the guts of your cell phone and shrinking it even beyond that to something that may be only a few grams in mass, but actually is built with little sensors, perhaps a little wireless receiver and transmitter, all in this tiny package. Then you attach it to a solar sail. In the case of this project, it's like a 1 meter solar sail. So a tiny little object with a 1 meter solar sail, and you hit that solar sail with enough energy to accelerate it to a few percent, or maybe even 10% of the speed of light. And if you could do that, then you could accelerate this tiny little payload by a very strong kick from lasers situated on the Earth to 5–10% of the speed of light. And at that point, you can get to the nearest star system in a couple of decades, thousands of times faster than our best spacecraft currently could do it. So, and that's pretty exciting. It's still a long time, but it's pretty exciting. So solar sail, powered by enormously powerful lasers, projecting their power into orbit from Earth, is the project's breakthrough starshot idea. Other ideas involve entirely new forms of propulsion that get beyond the chemical energy issues and inefficiencies I mentioned before. Nuclear power, efficient or fusion, would be millions of times more efficient than chemical energy, and that also in principle could get you to a few percent, maybe 5, maybe 10% of the speed of light. Another idea is to get the fuel you need as you go along by using a gossamer thin, essentially scoop, to scoop up the thin gruel of hydrogen and helium that exists in the space between stars or in the voids of the region between the planets, and use that fuel, which is essentially hydrogen, to power a fusion reactor. So the trick is not to have to carry all the fuel you need from the beginning of the journey, but you gather the fuel you need as you go along. So there are various ideas for plasma drives that are based on this kind of principle. None of these propulsion methods have been demonstrated even in the lab, let alone in orbit or in a scaled-down version. So these are visionary ideas. And the breakthrough starshot idea is also visionary. Their website lists, I think, something like 40 distinct technical challenges that would need to be solved for them to realize their vision and their dreams. And many of those individual challenges are extremely intimidating. But my hat's off to them for thinking about this, for actually trying to see what it might take to get to that goal.
All right, the next question is, if there were more planets in our solar system, when it was first created and some of them have been kicked out of the solar system through collisions, could it be possible to find out where they are by tracking back orbits, using models about how the solar system was formed?
So that's an interesting question about the archaeology of our solar system. So when we look at the orbits of the planets right now, they appear very regular. The eccentricities are low. The tilts relative to the orbital plane of the Earth and Sun are very small. They're very regular, and they appear to be very stable. If you take these orbits and play them forward in a computer for hundreds of thousands or even millions of years, nothing much happens. Nothing very interesting happens. But we're pretty sure, again, using computer simulations, that early in the history of the solar system, when the planets were being built, being formed from planetesimals, things were very violent. The orbits were not circular. They were fairly elliptical, so the collision speeds were quite substantial, and the destruction almost exceeded the creation of these large objects. Some things were getting ejected, some things were getting kicked into highly elliptical orbits or highly tilted orbits. All of these things were happening during the construction phase. It was kind of crazy. And things basically then just settled down after about 50 million years of planet building to the more regular orbits we know now. But regular doesn't mean boring. There seem to have been phases in the history of the solar system where the planets rearranged, where planets changed position. Basically, when the planets of the solar system go through what are called resonances, which are situations when their periods, the ratio of their periods equals the ratio of whole numbers, you can have positive feedback, which will pump energy into the orbit, and that can cause a planet to move, migrate inward or outward, and on extreme occasions could be ejected from the system. So even in a mature solar system, it's possible for planets to move around on occasion. And if you run these computer models I mentioned very far forward into the history of our into the future of our solar system, like 1 billion years, then all bets are off. Actually, things might get unstable again, and the solar system 2 billion years from now might not look at all like it does now. Another thing that astronomers have recognized with our solar system and others is that despite the huge distance between the planets relative to their sizes, making interplanetary space exceedingly empty, the solar system is dynamically full, which is to say, if you hypothetically just took a planet like a Mars, took a second Mars, and just tried to drop it between the Earth and the real Mars, or just took one of these big gaps between the planets and tried to add another planet, a small one, maybe even a Mercury or a moon-sized object, you could do that, and you can follow in a computer what would happen. And what would happen is you render the whole system or the inner part of the system completely unstable. And probably you either eject the interloper or you eject one of the other planets, or the planet's rearranged. Something quite impressive happens. And that's what the dynamicists or the astronomers who do this say mean when they say the solar system is full. There's no capacity to add any significant mass to this orbital situation without making it unstable. And of course, that means that if the solar system captured another object, the way we think, for instance, Pluto was captured from the Kuiper Belt, then that could also render it unstable. So although the solar system is mostly stable and mostly boring and definitely stable and uninteresting over millennia, it is not necessarily stable and uninteresting over longer time spans.
All right, the next question is from Stephen, who is actually on with us now, I believe, and also through email. Is the local group and Shapley supercluster moving contrary to the galactic expansion, leading to a massively dense region, which will be a small universe itself?
So the cosmic expansion, the Hubble expansion, as we call it, the expansion of the universe, it does apply overall and on the largest scales, but obviously it doesn't apply within a cluster because the cluster is bound by gravity. And as the question implies, there are regions of the local universe where there are substantial deviations from what we'll call Hubble flow. Hubble flow would be just the smooth separation of every galaxy from every other galaxy in a sort of uniform expanding universe. The local group looks like it's a weakly bound system. That is, the local group is the Milky Way, the Andromeda galaxy, and about 2 or 3 dozen dwarfs, the most notable of which are the Magellanic Clouds, large and small. The local group is falling into the Virgo cluster, and then there is a supercluster, so even larger concentration. So the local group is a few dozen galaxies, the Virgo cluster is a few thousand galaxies, and then the supercluster that all of these things are loosely a part of is tens or maybe even hundreds of thousands of galaxies on a scale of about 100 million light years. And it's actually difficult to decide, based on data we can gather now, whether these objects are what we would call bound. That is, whether this entire entity is exempt from the Hubble expansion because it's bound by its own internal gravity. It looks like at the scale of this supercluster, the thing is not bound, that it probably is loosely dissipating, although less than at the rate that would be true of individual galaxies in the Hubble expansion. So this is an active research field, trying to determine what scales of clustering of galaxies in the local universe are exempt or separated from the Hubble expansion because of their mutual interactions and which are not.
The next question is, I'm really interested in computer simulations of galactic formation and understand that they are intensive. Are you aware of any software accessible to the public for a home desktop type environment?
That's an interesting question, because the bar has come down on the best computer simulations. And in fact, they've moved largely, because there are a lot of research groups wanting to do this work, from supercomputer facilities like San Diego Supercomputing Center, which is the one we would use here in Arizona. They've moved onto the desktop. Not really the traditional simple desktop, as you might think of a very powerful PC, but what's called a Beowulf cluster. That's just a technical term for some people who basically ripped apart very powerful PCs and put together 64, possibly 128 super fast processors and ganged them together, added enormous amounts of memory, terabytes of memory essentially, and are just running it as a super fast number cruncher for doing gravity simulations. But even though that's quite a lot of work and quite a lot of money, these things are tens of thousands of dollars. They're not anything like the cost of a supercomputer. What's equally interesting is that running these simulations depends on clever software as well as powerful and fast hardware. And so basically there's very special chipsets that have been designed. Obviously astronomers individually don't get to design chips, but it turns out Intel and the other big chip makers have various markets that they sell chips which have parallelized software, such as for doing calculations of weather forecasting, and various other things. So there's a market for this, and astronomers use these chipsets that have sort of embedded software for speeding up the calculations. And one of these is called a GRAPE board. That's just GRAPE is an acronym, and I won't remember what it stands for. But that was one that has been not invented by astronomers, but used heavily by astronomers. I think these GRAPE boards only run a few $1,000s. So if you actually go online and research it a bit, it is possible for the cost of a super amped up PC to customize that machine so that you could actually run a pretty decent simulation, a simulation that would have taken a supercomputer 20 years ago or just been impossible 30 years ago. So that's very exciting. The bar has actually lowered on doing astrophysical simulations to the desktop, to sort of super powerful PCs, and also to a cost realm where individuals can do this work.
All right, so the next question is from David Cook via email, and this will have to be our last question for today. I read that particle pairs of opposite charge can emerge from a vacuum, but that they disintegrate very quickly in a puff of pure energy. How long do these particles last, and what happens to the energy produced?
Yeah, this is a prediction of theoretical physics that is indirectly confirmed, I would have to say, in laboratory and accelerator experiments. So the concept here, so it is completely possible and happens all the time in accelerators around the world for pure energy to produce particle-antiparticle pairs. So an electron has a rest mass of 512 MeV, million electron volts. And so if you have twice that amount of energy in a collision, you can create an electron-positron pair, electron and its own antiparticle, and they will flee the site of their creation. The electron will just continue and slow down and be trapped in normal matter. The positron will, as an antiparticle, will eventually annihilate with a normal electron and produce gamma rays. So producing particle-antiparticle pairs in collisions and accelerators is completely routine. That's a large part of what accelerators do. There's another effect that's a little more esoteric, more subtle, and I think what the question was about, which is called virtual pairs. So because of energy fluctuations, one formulation of the Heisenberg uncertainty principle involves the fact that the product of an uncertainty in energy in a reaction times the uncertainty in the timescale of that reaction is roughly equal to the Planck constant. And that's in normal physics units, that's a very tiny number. And that means that conservation of energy can be broken for incredibly short periods of time. And the corollary, essentially, of that Heisenberg uncertainty principle, formulated in terms of the product of energy and time rather than the product of velocity and momentum, is that particle-antiparticle pairs can come into virtual appearance, or can evanescently appear and then disappear for very short periods of time. And so these are called virtual pairs. So it's a prediction out of quantum theory. And like I said, it's very hard to directly observe these, because if it was in the case of my previous example, an electron and a positron as a virtual pair, the time scale that they come into existence is incredibly tiny fractions of a second. So the odds of observing this in any particular region, because this could happen anywhere essentially, it doesn't have to happen in an accelerator or a physics lab, the odds for difficulty observing this are enormous. But of course, these do have an effect, because these particles, for the tiny amount of time they come into existence, creates the possibility that the antiparticle will annihilate with a normal particle. and therefore change the situation, adding energy or creating pressure or some observable effect. So it is believed that virtual pairs do occur, that they're constantly coming into being and out, and then disappearing again out of the vacuum, out of the pure vacuum on incredibly short timescales. And that's a kind of stunning prediction of quantum theory. So that's an interesting way to end the subject, cosmology of quantum physics. Thanks for your questions, great questions as always, and we'll be back online doing this again in a couple of weeks.